Function notation is a way to rewrite a function in a way that communicates some extra information. So let's start by taking a look at a basic function, a linear function. To be specific, we may look at something like y equals 3x plus 2. So that's a basic function. In function notation, we would rewrite this as f of x is equal to 3x plus 2. Now what we've done is we've taken this y and we've replaced it with f of x. Now one important thing to realize is that f of x is one piece of information. F of x here is read as f of x. Okay, this is not f times x. Keep that in mind. This is not f times x. Okay, it's important to remember because when we start evaluating functions when they're in function notation, that's going to make a difference. Okay, so we need to understand this as f of x. It is one piece of information. The f of x, it is your new y value, or rather your new independent or dependent variable. A couple of unique things about function notation and how it helps us out is this. First off, it allows us to account for multiple functions at the same time. Here's what I mean by that. If we have, say, g of x is equal to 5x minus 2, and h of x is equal to 3x plus 6, and let's do k of x, let's do k of t, it makes sense, I'll illustrate why later. K of t is equal to t squared minus 5. Okay, so what I have here is three separate functions. Because I've labeled them in function notation, I've labeled them in a way where I can quickly reference them. For instance, if I asked you to work with the h function, you know that's what I'm talking about. Rather than saying work with the y equals 3x plus 6 function, all I have to do is say work with the h function because it has a unique variable given to it rather than just the generic y variable. So it allows us to identify which function we're working with if we have several different functions at the same time. The other thing it does for us is it tells us what our variable, our dependent variable, is dependent upon. In this case, g is our dependent variable and it's dependent upon x. X being the independent variable. Our h function is also dependent upon x. And our k function is dependent upon t. As you can see, that's the variable over on the other side of our equation. So function notation gives a unique label to a function and tells us what that variable, the dependent variable, is dependent upon. It references the independent variable. So with that, that's the first reason we use function notation, is to be able to clearly, quickly identify equations. The second reason we like function notation is it allows us to communicate more concisely and efficiently. For example, if instead of h of x equals 3x plus 6, I were to write this the way it's normally written as y equals 3x plus 6, if I wanted you to plug 2 in for x and solve for y, I would have had to say, using the function y equals 3x plus 6, plug 3 in for x and solve for y. However, with function notation, all I have to write is find h of 3. Much more efficient, much more concise. What does this mean? This means that I find my h function, okay, so it's referencing that I'm using this function, not one of the others. And what am I plugging in for x? Well, it tells me to plug 3 in for x. So finding h of 3 simply means take our h function and plug 3 in for the x. So that is 3 times 3 plus 6. Working this out, that gives us h of 3 is equal to 9 plus 6. Finally, h of 3 is equal to 14. So very efficiently we communicated which function we wanted to use, in this case the h function, and what value we wanted to plug into the independent variable. Here's what function notation also does for us. Have you ever gotten to the end of a problem and forget where you started? Function notation reminds you, how did we get this 14? Well, we got that 14 by plugging 3 into the h function. So it tells you what function it came from and what you had to plug in to get it. So again, another advantage of function notation. Okay. So working through a couple examples of this, let's take a look at this first set of examples. We have here f of x equals 3x plus 7, and we're supposed to find f of 4. Well, f of 4 simply means take our f function and plug 4 in for the x. So plugging 4 in for the x, simplifying that right-hand side produces f of 4 is equal to 12 plus 7. And lastly, that last step, f of 4 is equal to 19. So where did that 19 come from? The 19 came from plugging 4 into the f function. Let's look at it again. Here I have h of x is equal to 17 minus 5x. It's asking me to find h of negative 5. So h of negative 5 is equal to, well, I'm going to plug in my negative 5 in for x. So that's 17 minus 5 times negative 5. This produces h of negative 5 is equal to 17 plus 25. Lastly, h of negative 5 ends up equaling, what is that? That is, ends up being 42. So h of negative 5 is 42. Okay. Just so we solidify this, let's look at one more example. Here we have p of x is equal to 4x squared minus 12. Okay. How do we find p of negative 4? Well, we plug negative 4 in for our x. So p of negative 4 is equal to 4 times negative 4 squared minus 12. So that is p of negative 4 is equal to 4 times, well, negative 4 squared is 16, minus 12. So now we have p of negative 4 is equal to, let's see, 4 times 16 is 64, minus 12. So that's p of negative 4 is equal to 52. Now that's plugging a value into an independent variable. There's a couple more examples that we need to take a look at. And here's where they are right here. In this situation, it's set up a little bit differently. We have g of x equals 5x minus 23 here. And instead of saying find g of something, it's saying find x. So instead of plugging something in for x, we're supposed to find x when g of x is equal to 12. Well, if 12 is g of x and this g of x is the same as that g of x, that means I take this 12 and I plug it in for the entire g of x. Now remember, g of x is an entire piece of information. I'm not just going to plug the 12 in for the g, I'm replacing the entire g of x with 12. So it produces, it ends up producing 12 is equal to 5x minus 23. So solving this here for x, we add 23 to both sides. So 12 plus 23 produces 35 is equal to 5x. Now divide by 5, and we have 7 is equal to x. So what does x equal? X equals 7. So in this case, we're not plugging something in for x, we're plugging something in for the g of x. Let's look at that one more time here in the context of a quadratic. So in this case, j of x is equal to 26. So the 26 is going to go in to the j of x. That's 26 is equal to 5x squared minus 34. Solving for x, it's a quadratic, but since there's only one x value, we can go straight to peeling things away from the x. So that's going to be adding 34 to both sides. That produces, that's 60, is equal to 5x squared. Divide by 5. 12 is equal to x squared. To undo that x squared, to undo the square, we square root. Now when we undo a square with a square root, the other side must get that plus or minus. So we end up with, switching sides, x is equal to positive and negative square root of 12. We know we can simplify root 12 into root 4 and root 3, which then becomes 2 root 3. So our final equation ends up, or our final answer ends up being x equals positive and negative 2 root 3. And that's function notation. Again, a way to more accurately organize and communicate information.